So Austin, in the previous class, we classified the solution in two types. That is your ideal solution and then non-ideal solution. And we also saw that the non-ideal solution is of two types. The one which shows positive deviation and the one which shows negative deviation. Now, I already drawn a graph for this Rawls law, and this graph is basically for ideal solution. This graph is for ideal solution. So there will be another graph for non-ideal solutions showing positive deviation and showing negative deviation. If the line is straight, then it is ideal solution. Now I'm going to show you the positive and negative deviation. Just wait a minute. Okay. So in the previous class, the one, this is your on the left hand side, it is positive deviation, right? So for positive deviation, I'm going to draw a graph. Please do draw with me. This is the scenario, and you know that this will be your, just let me take a line from here up to here, and then again from here to here. So Austin, you can see this graph is for ideal solution. The one which I am plotting is this is for ideal solution. So as you know that this is your zeta A is equal to 1 and zeta B is equal to 0 here, and again zeta A will be equal to 0 and zeta B will be equal to 1. Since zeta B here is equal to 1, so this will be your P naught B, and zeta A is equal to 1, that's why this will be your P naught A. Okay. Now if you want to draw the non-ideal solution which shows positive deviation in so you know that the vapor pressure in positive deviation is more, so the graph will goes like this. Again the graph will goes like this, and again the total pressure will also be like this. So basically this is your total pressure PT, and this is for PB, and this is for PA. So this is a graph of which showing positive deviation, positive deviation. Now, if you want to have a negative deviation, so in negative deviation, the force of attraction decreases, and hence, if the force of attraction decreases, and hence the vapor pressure, the force of attraction in negative deviation increases, and hence the vapor pressure is decreases. So in that case, I'm gonna plot a graph in this way and in this way. So this, if this is your zeta A is equal to 1 and zeta B is equal to 0, and this is your zeta B is equal to 1, zeta A is equal to 0. Now, if you are going to plot this or mix this, join this two graph, if you are going to join this graph, this graph is for basically ideal solution. This will be for P naught B, and this is for P naught A. Now, if you want to draw a graph for non-ideal solution which shows negative deviation, the vapor pressure decreases in this way, and also the total vapor pressure also decreases. This is your PT. In the same way, you can go for this. This is your PB, and this is your PA. So this is a graph which shows negative deviation, which shows negative deviation. Let me know if you are done with this. Now, Humamuddin, are you there?
Yes, sir.
So, Humamuddin, this is the graph for positive deviation, and in positive deviation, that means basically it is a non-ideal solution in which the after mixing the solute and solvent, the vapor pressure decreases, and hence the force of attraction decreases, and hence the vapor pressure increases. So in this way, this is the graph for positive deviation, and in this you can see in negative deviation, when you are going to mix them, the force of attraction increases, and hence the vapor pressure decreases, and accordingly, this graph is for negative deviation. I think it's clear to both of you.
Yes, sir. Actually.
So can I change the slide?
Yes.
Okay. Now moving to the next topic, which is colligative property, and already we have done one of the colligative properties, which is relative lowering in vapor pressure. So please do write the topic. That is your colligative property. If we are going for this colligative property, so what is colligative property? Basically, property of any dilute solution, which depends upon the number of solute particles, not on the nature of the solid particles. Properties of a dilute solution which depends upon number of solute particles, that property is called colligative property. So I'm going to write those properties of dilute solution, those property of dilute solution which depend upon number of solute particles, and not on the nature of solute particles. That properties are known as colligative property. And there are four types of colligative properties. The first one is relative lowering in vapor pressure. Relative lowering in vapor pressure. The second one is elevation in boiling point. Elevation in boiling point. The third is depression in freezing point. Depression in freezing point. And the fourth one is osmotic pressure. So basically, there are four kinds of colligative properties. The first is RLVP, we can call it RLVP, that is relative lowering in vapor pressure. The second one is elevation in boiling point, and the third one is depression in freezing point, and the fourth one is osmotic pressure. Basically, this relative lowering in vapor pressure we have already covered in Rawls law, the second part of Rawls law, in which We mixed the non-volatile solute in a volatile solvent, then got a formula P naught A is Pa is equal to P naught A into zeta A, and accordingly we calculated that. I will just make you remind. Please do write it and then let me know. Let me know when you are done with this.
Done, sir.
Very good. Just wait a minute. Giving you a question. Okay. I'm just going to remind you this relative lowering in vapor pressure. If you remember, we did this part. Vapor pressure of, can you see the screen? Vapor pressure of solution containing non-volatile solute. Yes or no?
Yes, sir.
So you can see we derived a formula which was this PA is equal to P naught A zeta A. And here I just introduced this zeta A in terms of zeta B. And I told you after solving this P naught A zeta B will be equal to P naught A minus PA, which is lowering in vapor pressure. And if you are going to divide it by original upon P naught A, I told you this part is known as relative lowering in vapor pressure. So basically, for relative lowering in vapor pressure, as we already derived the formula, so we can directly write the formula. Zeta B will be equal to P naught A. You can call it original pressure or the initial pressure minus final pressure after doping the non-volatile solute upon the original or initial pressure P naught A. We don't need to derive it again because I already did this. And you should remember that this part zeta B is basically B is for solute. That at that time the B was for solute. So zeta B is for mole fraction of solute. Mole fraction of solute. P naught A is the initial pressure, pure pressure, and PA is the partial pressure after adding the non-volatile solute. Is that clear? So this is your relative lowering in vapor pressure. So this is the first, what we call first colligative properties. So just write it. You have already written it, and then let me know if you are done with this. And if you remember, yeah. So I'm going to ask you a question, a very easy question. There is two containers in which you can see this is the another container in which you are going to, this is your A, which is volatile solvent. This is your volatile solvent, and this is your non-volatile solute. And now you are going to mix them in a bigger container. So this will be your, just wait a minute, it's not working. A, B, A, B. As I told you, since this is your non-volatile, so it will be P not B or PB, whatever it will be 0 because it is non-volatile. Now, if you are going for this will be your, since it is since it is pure, so we are going to put P not A and it is volatile so that it will make some vapor pressure. And if you are going for this, there will be only PA. We are not going to talk about PB as it is non-volatile, so it will be 0. My question at this time, as I already explained this in the previous class of that previous lecture, can you tell me which one of the following is correct? Option A is P naught A is equal to PA. That means when A was pure, will that pressure will be equal to when it is mixed with non-volatile solute. P naught A greater than PA. And for the C, will that partial pressure greater than original pressure after mixing it? And option D is none of this. What do you think? Which one of the following is correct? Can anyone tell me? C is the wrong answer, Alan. So in the previous class, if you remember, see, if A is pure, all the surface molecule will be evaporated. But when you are going to mix non-volatile solute, some of the surface molecule or the surface will be covered by this non-volatile solute and it cannot vaporize. It will not create any vapor pressure. And that's why the number of particles that is evaporating in this case will be more as compared to this case, because some of the surface will be covered by non-volatile solute and hence partial pressure of A. Are you getting my point? Yes or no?
Yes, sir.
Now, the most important point is that if the vapor pressure in this is lower, if the vapor pressure after mixing a non-volatile solute is after mixing non-volatile solute decreases, that means the boiling point will increase or decrease. What do you think? If the vapor pressure decreases, that means force of attraction increases, and if force of attraction increases, that means boiling point increases. Yes or no? Austin
Yes.
and Homamuddin, please be clear with this because you will be always confused if it will not be clear to you. Austin?
Yes.
So what I want to say is that after mixing non-volatile solute, the vapor pressure here decreases. That means vapor pressure decreases. It is not easily vaporized or evaporating. That means the force of attraction increases and hence the boiling point increases. So the next topic that was basically elevation in boiling point, right? The next colligative property is this, elevation in boiling point. So what happens here, elevation in boiling point, as you know that when you are going to mix a non-volatile solute to a volatile solvent, the vapor pressure decreases and hence force of attraction increases and hence boiling point increases. That's why the topic is elevation in boiling point. That means if you are going to mix a non-volatile solute, the boiling point of the solution will be increased. So let me draw a graph and explain it to you. This is the graph between vapor pressure on the y-axis and temperature on x-axis. Now the graph is basically like this. This is the graph between vapor pressure and temperature, but the graph, this is for your, I will tell you, this is for solvent. This is for solvent. Let me do one more thing. Just wait a minute. See, this is the point where I will say this is your 1.013 bar, or you can call it 180. First of all, before explaining this graph, I'm going to explain what is boiling point. So first of all, I'm going to write the definition of this BP. BP here stands for boiling point. So the temperature at which vapor pressure of solution becomes equal to atmospheric pressure, that temperature is known as boiling point. If the vapor pressure of solution will be equal to the atmospheric pressure, which is equal to 180, that temperature is called boiling point. Now I'm going to show you, since as I told you, when you have pure solvent, then the vapor pressure is more. If the vapor pressure is more, that means the boiling point is lesser, T naught B this is, and this is for solution. If you are going to mix a non-volatile solute, the boiling point will increase. So this graph is for the this orange is for solvent, and this is for solution. And this T naught B is basically boiling point of pure solvent, which is volatile. And this TB is for boiling point of solution. Let me show you. This TB is boiling point of solution. So please do write up to this, and then I'm gonna write for. Let me know if you are done with this. This T naught B is the boiling point of pure solvent, and this TB is boiling point of solution.
Done, sir.
Are you done with this?
Yes, sir.
Okay. Now see, so this is the scenario of elevation in boiling point, and in this graph you can see when the solvent is pure, the boiling point of the solution increases. Now you can see I'm going to find the difference between these two boiling points. Delta TB is equal to basically the boiling point of solution minus boiling point of pure solvent. And experimentally we found that delta TB is basically directly proportional to molality, and here delta TB, to remove this proportionality, there is a constant that is known as helioscopic constant, Kb into m. M is basically, the small m is your molality. The small m is your molality. I'm going to write here, m is molality, and this delta TB is the difference in boiling point of solution and solvent. Also, this Kb stands for molar elevation constant. Molar elevation constant, or we can call it helioscopic constant. So please do write it. This is a formula, and you already know what is molality. Molality is the number of moles of solute per unit mass of solvent in kg. Are you done with this?
Done, sir.
Okay. Can anyone find the unit of Kb? If you have the formula, you can easily calculate the unit of Kb. Kb will be equal to delta Tb upon m. And you know that delta Tb is change in temperature, and temperature SI unit is Kelvin. And you also know the unit of molality, that is mole per kg. So the unit can be written as Kelvin per mole, Kelvin kg per mole, Kelvin kg per mole. This will be the unit of kb. Is that clear? So unit
Yes,
is
sir.
also very important. So you are going to write 18 gram of glucose dissolved in 1 kg. Calculate boiling point of solution if boiling point of water is 373 Kelvin and kb for water is 0.52 Kelvin kg per mole. Please do write. Are you able to solve it?
Yes, sir.
Okay. Just let me know when you're done with this. Any answer? Yes. I'm gonna explain. Just focus here. 18 gram of glucose. Glucose is a non-volatile solute dissolved in 1 kg of water. Basically, I forgot to write of water. So this is your solvent. This is your solvent which is given 1 kg. Calculate the boiling point of solution. We need to calculate TB. If boiling point of water, that means pure solvent is there, which is T0B, and it's given as 373 Kelvin. And it is also given that Kb is equal to 0.52. Now, delta TB has a formula which is equal to Kb into M. Now, Kb is directly given, which is 0.52 Kelvin kg per mole. This is the formula, this is the value of Kb. So you can directly apply this 0.52 into molality M. And we know how to calculate molality. Molality is equal to number of moles of solute upon mass of solvent in kg. So number of moles of solute, that is given mass, which is given 18 gram, upon molar mass is 180 gram. Glucose has a formula which is C6H12O6. This is the formula of glucose, and it will have a molar mass 180 and mass of the solvent in kg we need to put, and you can see the mass of solvent is 1 kg. So you can easily calculate the value. You can see the value will be 1 by 10 m, or you can write 0.1 m. Now, if you are going to put the value of m, you will be getting the value of delta TB as 0.052. This is the value of delta TB, which will be in Kelvin, because it is the difference in temperature. Now, we know that delta TB is equal to boiling point of solution minus boiling point of pure solvent. This is the formula, and we already have 0.052, and we need to calculate the boiling point of solution, which is TB. I'm going to put TB here, minus boiling point of solvent is given as 373, which is in negative. If you are going to move this to the left hand side, this will be in positive, and TB will be equal to, you are going to add this, so it will be 373.052. This will be the boiling point of solution. You can see it is elevated, increased. Please do write it. Let me know when you are done with this.
Done, sir.
Where? Austin, you are also done with this?
Yes.
Now do this question. Will you be able to solve it? Yes or no?
Yes, sir.
Just let me know if you are not able to solve. Option B. Very good, Huma. Austin, any answer from you?
B.
B. Very good. So, if you need any explanation, you can ask me. And if you know, just let me know. Just wait a minute. I'm going to give you another question. Okay, just please do this question. Will you be able to solve this question? Question number 1.
Yes, I'll try.
Okay. You can go for question number 8 as well. Please. Any answer for the first one? Okay, I'm going to explain. See, 2m, that means molarity is given of aqueous solution of NaOH in which the density is given 1.28 gram per centimeter cube. The molality of the solution, we need to calculate the molality. So for molality, you know that number of moles of solute we need here, as well as mass of solvent in kg. So if you look at the molality, what does this molality 2m means? 2m means 2 moles of solute. 2m means 2 moles of solute in 1 liter of solution. In 1 liter of solution. This is the volume. In 1 liter, you can write either, or you can write 1000 ml of solution. So you can easily look at this 2 moles of solute. That means number of moles of solute is calculated. That is your 2. Now we need to write mass of solvent in kg. As you can see, 1000 ml of solution. That means this is the volume of solution. That is 1000 ml. And you can write ml as 1000 centimeter cube if you want, because 1 ml is equal to 1 centimeter cube. And density is also given 1.28 gram per centimeter cube. This is the density part. So what I'm going to do, density is equal to mass upon volume. So if you are going to calculate the mass of solution will be equal to density, which is 1.28 gram per centimeter cube into volume, which is 1000 ml, or you can write centimeter cube. I'm taking centimeter cube because it is also given in centimeter cube. And now after solving it, you will get mass of solution is 1280 gram mass of solution, but we need mass of solvent. So how we are going to calculate? You know that mass of solvent will be equal to mass of solution minus mass of solute. So you can easily calculate the mass of solute. How you are going to calculate? Since number of moles of solute is given, that is basically has a formula. Number of moles of solute is equal to given mass upon molar mass. Number of moles of solute, that is 2 given, and mass we need to calculate molar mass of the solute, which is NaOH, has a molar mass 40. So you can easily calculate the mass of solute, that is 80 gram. that is 80 gram. Now, if you want to calculate the mass of solvent, you can easily do this by subtracting this 1280 minus 80. This is the mass of solution, this is the mass of solute, and you will be getting the mass of solvent as 1200 gram. So put the value here, 1200 gram in kg. If you are to convert this in kg, it will be 1.2, and after solving it, you will get 1.67 m. So the answer that you will get is your D. Isn't it easy? So if you will go step by step, you can easily calculate the answer. Austin and Humamuddin.
Yes, sir.
Okay. So just let me know when you are done with writing this. Are you done with this?
Yes, sir.
Okay. So this is it for today. This question you are going to solve it from home. Question number 8. Please do write it. And also in the next class, we are going to discuss about depression in freezing point FP, and then osmotic pressure. Osmotic pressure. And in the next week, we are going to complete this syllabus. And also, please do try NCRT. We will discuss that as well. Let me know when you are done with this. Are you done with this, Austin?
Yes.
Mahmoudin? Okay.
Yes, sir.
So this is it from my side. I'll see you in the next class. Okay. Thank you.